Okay, in the last video we saw how to define the notions of flux and work and in terms of vector fields and line integrals. And now let's do a couple example problems that show how to actually, compute these mathematically. So in this situation we've got a motorized toy boat that propels itself forward at a constant speed. It's connected by a stiff rod to a pole in such a way that it drives itself counterclockwise around the point 0, 0 in a circle of radius 2. All right, so it's essentially just the boat kind of goes around in a circle like so, and the radius is 2. Okay? And then what's going on is there's water that's being pumped out from the point 0, 0 in such a way that anywhere else the flow is given by this radial vector field. So it turns out the flow kind of looks like that. All right? And so as the boat goes around the circle, the water pushes against the boat, and we want to know how much work does the water do in propelling the toy boat around one loop of its path. Okay, so let's see if we can set this up. First, the position function is 2 cosine of t, 2 sine of t, because it was a circle of radius 2, so that's the parameterization of a circle of radius 2. And that's for t's between 0 and 2 pi. It takes 2 pi seconds to go around the circle one time. That means the derivative, r prime, the velocity is essentially negative 2 sine of t and 2 cosine of t. That's the velocity. And the vector field F, what did they say the vector field was? Y over x squared plus y squared plus y squared. So here's x over x squared plus y squared, and then y over x squared plus y squared. So that's the vector field. Okay. In terms of our parameterization, if we put this into terms of t, well, x would be 2 cosine right there. So that's 2 cosine of t. The y would be 2 sine of t. And x squared plus y squared, well, that's going to be cosine squared plus sine squared, which will be 1, except it's 2, so the radius will be, it'll be 4. The radius is 2, but x squared plus y squared will be 2 squared, which is 4. All right, so there's my vector field in terms of time t. And they wanted to know the work. Right? So the work is the integral over the curve of the vector field dotted with the tangential direction, ds, right? And once you work that out, we're going to go from 0 to 2 pi. That's our time. F would be, well, we just had this, 2 cosine of t over 4, 2 sine of t over 4. And then TDS, remember, that's going to turn out to be r prime dt, and we just computed r prime. That's negative 2 sine of t, 2 cosine of t, dt. And so now it's really just a Calc 1 integral. It turns out to be, what, negative 4 over 4, that's negative 1. So negative sine of t cosine of t, plus 4 over 4 is 1, sine cosine, so plus sine of t cosine of t dt, but that's actually just 0 dt from 0 to 2 pi. And the integral of the 0 function is just 0. Oh, so how come we got 0 here? Well, go back to thinking about what's really going on. The boat's going around this way, around this circle, which means at any point it's going there. But this is a radial vector field going there. So was the vector field ever pushing the boat along the path? No, it was always orthogonal to the path, which is why this dot product was 0. So it was basically 0 circulation or 0 work being done by the water on the boat in the direction of travel. Now, if we had computed the flux, well, then we would have gotten the exact opposite thing would have happened, where the normal vector would have been in the same line as the flow of the water, and so when you dot product them, you would get a positive number, and you would have added those up, and you would have gotten a positive flux. So that would have just been doing n here, right? Putting n there, and then when you put n in, you would have had y prime negative x prime according to this formula right here, right? Okay. All right. So let's do another example. And in this one, well, that's what this example is. Let's actually work it out. So same situation, same vector field, and then they just want to know what the outward flux of the water is across the curve there. So, okay, so the flux then is the integral of the curve on the curve of the flow of the water dotted with the normal vector, not dt, but ds, right? So there's my function, multiplying it times that, but that's going to turn into integrating t from 0 to 2 pi of the vector field dotted with, what? It's going to be y prime negative x prime dt, right? And ds becomes this thing dt. Okay, and now what was x? X was 2 cosine of t, y was 2 sine of t, so we're going to have my vector field. That should be the same vector field we had before, right? 2 cosine of t over 4, 2 sine of t over 4. So that vector field is 2 cosine of t over 4, 2 sine of t over 4. Y prime is 2 sine of t. X prime is 2 cosine, but it becomes negative. Oh, I'm sorry. No, that's wrong. X is 2 cosine, so x prime would be negative 2 sine of t, and y prime would be 2 cosine of t. So then y prime would be 2 cosine of t, and negative x prime would be 2 sine of t dt, right? Negative x times negative 2 would be 2. And then that's from 0 to 2 pi. So now if I integrate from 0 to 2 pi, I'm going to get what? Cosine squared plus sine squared dt. Well, of course, cosine squared plus sine squared is 1. And then I just get t evaluated from 0 to 2 pi, which is 2 pi. So this problem has a flux of 2 pi, which is what I was kind of explaining a second ago. The vector field is pushing against the boat. It's pushing out, the water's sort of flowing out of the curve, so we call that flux across the curve. And we parameterized it counterclockwise, so that's giving us the outward flux. All right, so there's a couple example problems showing you how to do circulation and flux for line integrals.